So in this video, I can prove to you two things. This video and all of this is the culmination of about 2 months of research and starting off with a simple problem and a simple observation. What I can prove to you up front is that one, the laws of physics must arise external of Euclidean space, and two, that the incorporation of curvature itself, that the curvature itself, the space curvature, is a part of the laws of physics. And so we'll dive very specifically into both of these concepts. Starting off, I think kind of the first place to start off with this is how exactly do I come up with this observation and where do I start with from this, right? So I've been, if you watch any of my videos, really heavy into reinforcement learning, playing around with that and understanding exactly how reinforcement learning works for AI models. And then through that, I've essentially understood kind of the mathematics and framed the mathematics of how exactly reinforcement learning works for myself. And essentially how I frame the mathematics in my head is that you create a Gaussian space and then you simulate probability within that Gaussian space utilizing Monte Carlo probability, and then you create the variables within that space, and then those variables within the space create essentially the interactions within the environment, right? And then you use algorithms to learn the environment depending on the situation of the environment. So if you want to set a designated reward mechanism, then you would use Q-learning algorithm and set DQN networks, etc., and build out that way, right? But so kind of the overall concept, I start fixating on the box, essentially, right? This Gaussian probability space. And then it intrigues me because this Gaussian probability space operates differently than other mathematical spaces that I've known, right? Like geometric spaces and et cetera. And then so just inherently, as I start playing around with these spaces, I notice that there's a difference, that when I put mathematical space in this box, it operates differently than if I don't put it in the box. And that's just, like to me, an observation that a 5-year-old could make as they're going through these things, right? But then the second observation that I make within that is that the physics are different within the box, but the physics exist only in the box, right? So, meaning that I can utilize the laws of physics in Gaussian space, in Gaussian probability space, which is intriguing to me. Like, to me, that kind of starts throwing up kind of like red flags to me as a layman, right? Why can I do that? Like, how? What is the mechanism that allows for the laws of physics to all of a sudden appear in my mathematical space, in this space, in this box, this Gaussian box that I make up? And it's completely imaginary, and I make up this Gaussian box in this Gaussian space, and I define all the parameters of it. And then when I do that, all of a sudden physics is in there. And if I don't do that, there's no physics in there. And I don't know, like that just rattles in my brain. And then so I start playing around with that, and I start analyzing that. And then so the best way to show this in video format is not through the mathematics, but through experimentation, right? So I start experimenting with this and experimenting with curvature and Euclidean space versus hyperbolic space, and how I frame this easily in my head, just very simplistically, right? If you're like a layman in these terms, you think of Euclidean space as mathematical infinity. It's all the same, it's all uniform, and it's all infinity, like a straight line that goes from 0 to infinity. And that's Euclidean space. It's all the same, right? And then in this space, like you have triangles and rectangles and squares, etc., right? Like all of your different shapes. Your geometry lives in this space. And then outside of that, separate from that, if you create a box, right? So in order to create a box of space, you have to bend the space. So if you bend the space into a box or into a structure, then the properties of that are different. And then so this is the same code, right? And then so essentially what I do is I create agents, and then I just have them go throughout space. And then so in Euclidean space, they just go throughout the infinity space, and then this is what they do, right? But I make external box within Euclidean space. So then we can map it, right? And so it's the same box. It's 2 by 2 square in Euclidean space and 2 by 2 square in hyperbolic space. And then when I do this, here's the simulation. Very straightforward. What I would expect from Euclidean space, and then here's what I get from curve space. And then so what's here? These timestamps are the lighter blue and the blues are later. So we can see that what happens is it's dispersing outward, which makes sense. That's exactly because the curve is on the outside, right? So they're dispersing towards the curve that I made in space. They're dispersing towards the edges of the box, in essence, and that's expected. And then also too, what we can see within this, if I do further analysis here, and we look at these kind of metrics. Clustering increases in these hyperbolic spaces, and I can prove that. So what I can prove just through this code here, very specifically, is that in this curve space, so just by taking infinity space and then putting a bend in it, right? that bend, but by simply putting the bend, that increases entropy, decreases variance, and increases clustering capabilities. And those three concepts are directly corollary to the bend, meaning that if we're looking at this first one that we're looking at here, we have a small curvature, right? And then so we have our variance, our entropy, and our clustering. And we can see, we look at this in comparison, we have a curvature of 0.05. compared to our curvature down here of 0.30, and there's a significant difference, right? Decrease of variance, increase in entropy, and increase in clustering behavior compared to that 0.05. And then, so what are the exact mechanics behind this? I don't know, but I can prove the corollary and the correlation there, right? And I can formalize this further. I can formalize this mathematically as well, and that's what I do here. So if you are not a Cody, you want to examine this all from the mathematical aspect and pick this apart and prove it wrong mathematically, then here's 19 pages of math that essentially back this up and frame this as well, right? So essentially giving you both ways, both arguments, and also I formalize it into logical form as well. And then I give you all of the experiments in this paper as well, right? So like all of the experiments that I just went over here, you have them kind of more listed out in detail in this paper. And then you also have the mathematical formulation that arises from these experiments, which proves the secondary correlation of the argument, which is that curvature itself is somehow related to the laws of physics. And that's where I'll leave that at, right? Because that's where I leave this. Actually, I'll show you one more aspect from this, right? So what does this mean in real world terms? Like what can you do with this, right? And I mean that's the honest bottom line that I want to get into. And I'll I can tell you very explicitly and very honestly, what my ultimate goal is with this, right? So my goal and my hypothesis within this is that by utilizing this, and we can find a mechanism, if we can find a mechanism to write to hyperbolic space, then essentially we get access to what I would term as infinite storage, unlimited storage. How exactly does the brain store memories? How exactly can you store so much in your brain? I don't know, right? No one knows. But so this mechanism here is the best mechanism that I have seen that could theoretically allow for this, right? So, I mean, this part here where I'm getting into on this, this is essentially literally where Stephen Hawking leaves off with his research, right? Essentially, so with all of what I've proven here, the corollary and the argument that I make from this is essentially that I can utilize hyperbolic space, and then I can mathematically reconstruct physical space and hyperbolic space, right? And then so the mathematics should be the same then. And then so if that's true, then in physical space we have event horizons, and then so in hyperbolic space, if this is all true, there should be a hyperbolic horizon as well, right? Which happens to be true. There is a hyperbolic horizon that exists within math. This is very known within calculus, etc. Right? And this is all of this is utilizing this, right? This is this math that we're looking at here. This is all reliant on a hyperbolic horizon, and then so. Where Stephen Hawking's research ended was the thesis that black holes can write data to the event horizon. And then, so if that's true, if a black hole can write data to an event horizon, then an LM model can write data to a hyperbolic horizon. And then so that's what I am experimenting within this, and I kind of prove out at this point that's true. that the models can write data to this hyperbolic horizon, and that it like the best way that I can think to frame this and what this essentially equates to and how it works out. When you look into this, it's kind of like defragging, right? Like it's like defragging a hard drive is the best way that I can look at this, right? And through my experiments, I have a lot of experiments. I look at like a good example. I'm trying to find one, but so within this, what we see is that the hyperbolic space essentially gets condensed within this, right? And within this, we can utilize this space, and the LM model can utilize this space to condense the data that it has. Like it's fill in space, right? Like within a hard drive, very common. If you can increase the space within a hard drive by condensing the data within the hard drive, right? It doesn't increase the physical capacity of the hard drive, and that's what we're doing in this instance as well. We're just compressing the data. It doesn't increase the physical capacity, but it increases the storage capacity. And then we can keep compressing and compressing and compressing the data because we just write to the the hyperbolic horizon in this particular instance, the mathematical horizon. We can do that via all of the math that I'm checking out here. So I'll leave a link to these collabs, to this research paper, to everything here. Feel free to rip it apart. I'm not going to submit this academically, etc. So like it's going to be hard to find this particular research, but I've formalized it. Here it is. If you like this type of content, please like and subscribe. Thank you very much.